All right. Once again, thank you for joining on, well, at least where I am, it's a Friday afternoon, and I appreciate you taking the time to join today's webinar. This is the second in a series of webinars on Friday afternoons that I've been trying out. I've been traveling a lot, and it seems like the only time I'm home or in the office is on a Friday afternoon, so a good time to do a webinar. So today's webinar topic is called Lessons Learned from Actual Control System Security Incidents and Assessments. A bit of a mouthful, but I wanted to give this a title that was pretty descriptive. I just got back from Nashville, Tennessee, where I presented this a couple times at the Emerson Exchange. And so it is exactly what the title says. It's a number of different lessons learned from going out and doing actual control system security assessments, and then it's also coupled with related information from actual control system security incidents. So hopefully the idea of this is to give you an idea of course, we're going to walk through a process for how to secure your systems, but then also learn from actual incidents and assessments, as it says. So my name is John Cusimano, as I've said. I'm with Exida. I'm the Director of Security Solutions. My background is in industrial automation, primarily, but with an emphasis in safety systems and cybersecurity of control systems. My background is working for different automation end users and automation suppliers, and I'm fairly active in a number of industry associations related to control system security and control system cybersecurity and safety. Exida, if you're not familiar with us, is primarily an engineering consulting, testing, and certification organization focused on helping our clients improve the safety, the security, and the availability of their automation systems. That's pretty much our sole focus, and as you can see, we have offices in numerous countries around the world. I'll get right into the content of this presentation, but start off quickly by talking a little bit about why control system security is important, and really how is it different than traditional IT security. There are a number of differences, but the primary difference is that control and/or SCADA systems, whatever you choose to call them, control real-world devices and processes. If they fail to perform or act unpredictably, it can lead to some pretty serious consequences, such as loss of production, loss of service, producing off-spec or dangerous product, environmental releases, and other that could lead to sickness, injury, death. Also, physical equipment damage is missing from this list, but that could also be a consequence. So it makes control systems quite a bit different than your general IT type of products, even though a lot of the same technology is used. So some of the techniques that we use to secure our IT systems are also very applicable to control systems, but some things are quite different, and we'll go through that in this presentation, but that's one thing that I think is very important, because there's a lot of IT security consultants that know that business quite well, that also offer services in their control system security, and so it's important that you work with a company that knows both control systems and IT security. I would imagine that if you're attending this webinar and you're interested in the topic of control system security at all, or have followed it at all, that you have heard of Stuxnet. Stuxnet was malware or a virus that was discovered well over a year ago actually was in the wild, if you will, for almost 2 years, and it really had a pretty big impact on particularly on the control system community, because it's the first time that we've seen a deliberate attempt to use industrial automation systems, control systems, for to actually cause harm to a process, and to do so in a way that actually took over not only control of the Windows computers that were attached to the control system, but actually the control system itself, and actually were able to modify or change the process in a way that damaged equipment by using the control system to do that, and also did it in a way that was able to hide its behavior or the changes it made to the system from the user. So I don't want to talk about Stuxnet in detail today. What I want to talk about is the impact that Stuxnet has had on the control system community. And there's three main things. Number one, it provided proof of concept, and some might say a blueprint for other hackers who might want to do the same thing or similar variants of Stuxnet. Prior to Stuxnet, certainly the control system community had talked about and was concerned about the potential for viruses and malware like Stuxnet, but we had never seen anything, certainly not to this level of sophistication and complexity. So with the emergence of that and the detailed analysis of Stuxnet, it's no longer a question if this can be done. It can be done. Number two is it's really raised a high level of awareness at much higher levels in the organization than previously existed. Control system engineers and the control system community have been talking about cybersecurity incidents for almost a decade, but most of that discussion never made its way even up to maybe as high as middle management, but very rarely would have made its way to senior management and executive management in most organizations. However, after Stuxnet, almost all most corporate executives, certainly those that are involved in owning and operating industrial plants that use automation systems and have potential hazards, have probably heard of or read about Stuxnet because it showed up in major media outlets like Wall Street Journal and New York Times and other mainstream media, CNN and so on. It's also exposed regulators and the public to the potential dangers of cyber attacks, so creating much more pressure on organizations to react and make sure that their systems really are secure. And lastly, the third impact of Stuxnet that I've identified is it's really opened up a market, if you will, for people who would describe themselves as security researchers, those that do unsolicited testing of products, software products generally, to find and exploit vulnerabilities in those products. Security researchers have been working in the IT area for a long time, finding and reporting vulnerabilities to companies like Microsoft and Adobe and so on. And are a large part the reason why we have Patch Tuesdays and so many different security patches coming out, because of course in part sometimes the manufacturers find the vulnerabilities and fix them, but more often than not it's actually a third party, such as a security researcher, that found the vulnerability and reported it to the organization. And a number of different reasons that people are motivated to do that. But nevertheless, what the impact of Stuxnet is that the security researcher community, like for example, this week there was a conference called Hacker Halted, where there was an entire track on SCADA. So the black hat hacking community is quite interested now in SCADA. The Black Hat conference also had featured numerous papers on SCADA. So it's cause for concern, particularly if you own and operate, or even if you're a manufacturer of control systems, because there's now so many very smart people, or at least there's quite a bit more of these very smart security researchers that are paying careful attention to the industrial control system products and researching, looking for vulnerabilities, and quite honestly, the opportunities are quite ripe for them. A lot of products have, it's not very difficult for them to find vulnerabilities in a lot of industrial control systems products, because this just wasn't an area of focus for industrial control system community until recent years. So it puts our market, the control system market, really right in the crosshairs of, and we certainly can no longer hide from this topic of cybersecurity of control systems. Of course, the government has been aware of this for quite a while. Certainly, after 9/11, the regulatory efforts became much more apparent around this topic. Three main branches of the government have regulatory programs in place that address control systems cybersecurity. The first is the Department of Homeland Security. In addition to running a very good program called the Control System Security Program, which is more of an outreach awareness program, and they just hosted a conference also this week on the West Coast called the ICS JWG, Industrial Control System Joint Working Group. But in addition to that awareness and training program, there's also regulations mandated by DHS for the chemical industry called the Chemical Facility Anti-Terrorism Standards, which deal with a lot of different aspects of securing chemical facilities, particularly very dangerous, what they would call Tier 1 chemical facilities. But part of it is also addresses cybersecurity of those facilities as well. If you're in the electrical industry in any way, electric utilities, generation, transmission, distribution, you would most likely be aware of the NERC-CIP standards. NERC stands for North American Electric Reliability Council, and there's a series of standards called the CIP standards, Critical Infrastructure Protection, that are actually mandated by law in the U.S. by the Federal Energy Regulatory Commission. And those deal with cybersecurity of industrial controls. And lastly, if you're in the nuclear industry, then you should be well aware that the NRC also has pretty strict regulations around cybersecurity. But you may also not be in an industry that is not regulated, or such as at the moment water, wastewater, food and beverage, many manufacturing industries, oil and gas, and but still understand and appreciate the business risks and want to do something proactive about improving your cybersecurity posture. And that's where industry standards come into play in particular. Three in particular I want to bring your attention to. Actually, the first two are very largely one and the same. There's the IEC 62443 series of standards, which is very related to the ISA 99 series of standards. I will show you on the next slide a little bit more specifically about how those two efforts are integrated. And then lastly, the U.S. Government National Institute for Standards and Technology, NIST, has published a guide to industrial control system security that particularly applies to federal systems, but there's very good information in there, and much of it has been incorporated into the ISA/IEC body of work. So I said this is more detail on this IEC 62443 ISA 99 series of documents around control system cybersecurity. As you can see, there's actually 9 different documents that have been defined and are either published or being worked on, and they are divided into 4 main categories based on the audience for these standards. The first tier at the top, called General, is exactly that. It's general information about terminology, concepts, models, glossary of terms, metrics, and it's good general information about the topic. The second tier in green, labeled Asset Owner, is a series of standards targeted for the companies that own and operate industrial control systems. Rumor has it the first 2 of these are actually going to combine into one. I'm not sure if that's official yet, but establishing an industrial automation or industrial control system security program is a published, available standard, both by IEC and by ISA. And the latter work to the right of it, operating, is a work in progress that have been told will be integrated with the first document. There's also a document in the works for patch management, and a new document. This is a body of work that came from outside the ISA community and was contributed by a group of end users in Europe, called Certification of Industrial Control System Supplier Security Practices and Policies. The next tier down, System Integrator, has to do with exactly that, those people that integrate control systems, whether it be a third-party system integrator or a manufacturer that also provides integrated control systems, or even the end user that's doing their own integration. And there's 3 documents here. And then lastly, the bottom tier is aimed at the component provider, those companies that are actually designing and building and manufacturing control system components, such as controllers, network switches, software, and so on. 2 standards here, one having to do with product development security requirements, and the second with technical security requirements for those products. Sorry that was a little bit lengthy, but it's important to understand the structure of the documents that are available, particularly for as we go through the rest of the presentation today. I'm going to be talking about assessing actual control systems in the field. And so when we do that, we generally follow the ISA, the 990201 document, which would also be the 62443-2-1, called Establishing an Industrial Control System Security Program. The document covers a lot of different topics, from risk analysis to policy, organizational awareness issues, to technical countermeasures, to implementation and maintenance issues. Rather than present it to you in that structure, which is a bit more complex and would take quite a bit of time, we've simplified the topic down to 7 main steps. And these all do map to items in 990201. It's just a alternative way of presenting to simplify this down to 7 key things that we think are very important, or key steps that we think are very important when securing control systems. And those 7 steps are, as listed here, starting with assessing existing systems to understand what it is you have and where you are and where you need to be. Then documenting policies and procedures, training your personnel and your contractors on those policies and procedures and other technical training. A very important part is segmenting the control system network, or building layered defenses, or defense in depth into your network. controlling who has access to the system, both physically and logically, and hardening, security hardening of the components of the system, making sure that you only have those features and functions that are absolutely necessary to perform the function of the system. And then lastly, monitoring and maintaining system security. So the balance of the presentation today will cover each of these 7 steps, and as we go through, I will talk about also not only what the step is, but also lessons learned in performing actual assessments. So the first one is assessing existing systems, and this is first for a number of reasons. Number one, this really does need to be done first before you do anything else. You really makes sense to understand your own systems and your own risks, and compare your current practices, your designs, your policies against these standards and best practices. So you can identify gaps and estimate the magnitude of the gap in terms of the amount of risk associated with that, and then provide management with recommendations for closing those gaps, particularly in terms of a formal, at least semi-formal risk assessment that would show management that you've done due diligence, you've looked at the problem, you've assessed the risk, the magnitude of the risk, and you can make recommendations that make sense, both financially as well as can be justified financially and also by the amount of risk reduction. There's a number of ways to do this, to assess the risk and assess the current status of a control system. We at Exeter have been using a modification of a technique used in software development. We like this quite a bit for doing risk assessment from a security standpoint. It's called threat modeling, and it's a technique that comes from software development. If you joined my webinar last Friday, it was all about threat modeling. And basically what we do is we take a look at but this threat modeling can be applied not only to software development, but also it can be scaled to be applied to system analysis as well. So we start by taking a look at the control system under question. Here's a very simple network diagram of a couple controllers, a couple workstations, an industrial network, and a firewall, and identify the boundary of what you're trying to assess, and where things are trusted and within the control system, and where you're going into more untrusted territory, if you will. And identify then the entry points into this system that you're going to evaluate, whether that be ports on the firewall, other communication ports like those that might be directly on the controllers, communication ports built into the workstations and servers, such as USB drives, CD-ROM drives, and also entry points such as open ports on network switches where somebody might either deliberately or accidentally, they may be authorized to do so, but plug a laptop into a network switch, making a temporary connection that could also be an entry point. And once you've go through this model, look at the entry points, then you need to identify threats, and there's a number of different methodologies based on threat modeling to go through and systematically identify threats, which I talked about last week. But once you do that, you identify, you create a table, you identify your threats, the vulnerabilities that could be exploited by those threats, any existing safeguards that may be in place, and the consequences of those, and apply a basic risk matrix methodology where you classify the severity of the consequence and the likelihood using semi-quantitative values like low, medium, high, very high, and apply that to a risk matrix that would give you your resulting risk. I'm not going to go into any more depth today on this topic, but that is one of the we find that to be a very good way to go through and do a risk assessment, but not the only way. So, having done a number of different assessments of control systems at facilities across a variety of industries, everything from water, wastewater to oil and gas and chemical and food and beverage and so on, a few common findings emerge. One is that in general, most companies are not doing any kind of formal security risk assessment. But that's not entirely true. There are a lot of companies that are looking at this actually right now, particularly large major oil and gas and chemical companies that have either already adopted security risk assessment methodology or are working on doing so. And I attended a presentation at the conference where an end user got up and talked about his experience doing risk assessment and the value of doing so and being able to really identify what are the high risk areas and to be able to make a very good case to his management about what needed to be done and why, and to justify the expense. But in doing assessments, we do see a lot of issues that are kind of clearly the result of having not gone through this exercise. Because one of the problems we see with not going through a formal risk assessment and just jumping in and applying security is that we see overcompensation in some areas and undercompensation in others. In other words, the time and effort and money may, in many cases, be not properly applied or not applied optimally to reduce risk. So one example that comes to mind is a food and beverage manufacturer that had done a great job of securing their DCS servers. They were all in a locked room managed by the IT department, required card reader access to enter, and very few people actually had access to the DCS server room. Yet a couple engineers had complete development stations on their desks that were outside of the secure area that were pretty readily accessible, and they were connected both to the process control network as well as to the internet. So here's an example of a bit of disparity in terms of a lot of effort was put into securing the physical servers, but then logical connections to the system were effectively wide open. The second item on the list of 7 things is 7 steps is to document policies and procedures. It's very important, particularly after you've done the risk assessment. Should be apparent, hopefully, where your risk areas are and how you're going to manage them. And some things can be and should be managed using technical controls that can be enforced, and some things can and should be managed through policy and other enforcement mechanisms. But either way, it's important to document for your employees, your personnel, your staff, your contractors, really what is expected, what the company has decided upon in terms of policies around control system security. And maybe even more important is how those policies may be different than the policies that apply across the board for general IT office environment, or how they may need to be modified. An example of that might be in patch management, whereby Microsoft security patches are probably, in many companies, are automatically retrieved by IT and pushed out to everybody's laptop automatically without necessarily your consent or asking, other than maybe for scheduling purposes, asking for your approval, which requires, of course, most of the time a reboot of the machine and so on. Those kind of, that same level of automated, mandatory patch deployment cannot be applied in most industrial control systems for a number of reasons. Those patches need to be tested and approved first by the control system manufacturers. They should also be tested and approved by plant personnel or corporate personnel. If it requires a reboot of the machine, which is often the case, that can't just be done at any time. So that's just a few examples of some of the differences between patch management in a control system environment and in the IT environment. So it's important to document those policies so that everybody understands what the differences are and why they're important. So some of the things we found when relative to policy and procedure when performing these assessments is that most large corporations do have written, documented IT security policies, but most at this point either don't have or are working on writing control system specific policies. There are a number of organizations that certainly that we're aware of that are either have documents in process or available, but many companies still don't have any documented policies that are specific to control system security. And that can cause for some problems. For example, one company we're at had been using a Unix-based DCS and was patching that on a pretty regular basis, as often anyway as Unix patches come out. But they had recently moved towards a Windows environment and for their DCS, and they did not have a patching program in place there. And so part of that can be blamed on just not having a consistent policy in terms of, you really do want to write your policies. This is a good example of making sure your policies really should be platform independent. Policies shouldn't say, well, for brand X we're going to do this, for brand Y we're going to do this. Should state in general terms what your policies are, and then have more specific procedures that might get to be platform specific. Other areas with policy and procedure and some of the differences between IT policies and control system policies. One example, and this is actually becoming quite common, we're seeing this, is that the boundary between the control system and the IT network, those switches that establish that boundary, many times are managed, are almost always managed by the IT department, and many times that service is outsourced. And so one example we ran into at a facility was switch was managed by an outside IT provider, and effectively any employee with a valid charge number could request a change to the access control lists in that switch. And when we did an investigation after this company had an incident, we found a large number of unnecessary access privileges being granted purely because somebody had opened a ticket with this IT security provider. Another thing is we often see standard IT images on servers and workstations, which often include many applications that really just aren't necessary for the control system environment. I said I'd give you some examples of some actual incidents related to these topics, and one related to policy and procedure here is an example of an incident where a disgruntled contractor intentionally disabled pipeline leak detection for 3 oil derricks off of Long Beach, California. The basic policy problem here was that the company didn't disable his access to the system after he had been terminated, which seems like a pretty simple, straightforward thing to do, but unfortunately that is often is overlooked. And actually, more recently in this year, another incident very similar with a former IT employee who gained access to the system after being terminated and used some software he had installed previously to be able to wipe out 15 virtual machines that represented actually 88 different servers, and crippled the company from being able to manufacture for several days, resulting in nearly $1 million in losses. Step number 3, then moving on, is to train your personnel and your contractors. Once you've established your policies and procedures, you want to train your personnel, your visitors, your contractors, anybody who has really a business reason to interface with control systems should receive at least some basic control system security training. And we're big proponents of role-based training, having that training vary depending on the role of the person, whether they're a contractor, a new hire, operator, engineer, maintenance personnel, so on, management. And so one of the things we're working on with some of our clients is role-based training models. This is just a screen capture, or clip, if you will, of a matrix we're working on with some of our clients to describe by role, which is the columns, the material needed to be understood in a number of categories, and this is just a partial example. So what do we see when we do assessments? We see that most large corporations do offer and require information security training, or basic IT or IS training, teaching employees really how to be good stewards of the company's information, to lock their computers, to use strong passwords, to change their passwords regularly, and so on. But very few offer or require control system security training at this point. Though again, like the policies and procedures, there's quite a bit of activity in this going on in this area, with a number of companies are working right now on developing and rolling out training programs. But sadly, still, many plant personnel are still very much unaware of the risks of cyber incidents. And to give you an example, I was recently doing an assessment at a water wastewater facility, and I was authorized to go around and collect the information I needed by plugging in a secure, clean USB stick that was virus scanned between computers to go collect data. And but I was really surprised because I was going around this facility unescorted and plugging my USB stick into their computers, and not one person asked me what I was doing or why I was doing it. The staff and personnel didn't seem to see anything, didn't seem to have any concern about that activity. Another example is recently at another facility I was at, when we did an assessment. We found a VNC server for remote access on one of the engineering workstations, and when we asked why that was installed, the management we were working for said they didn't know why, and when they investigated, they found out that one of their employees had allowed a vendor to install that so the vendor could have remote access. So again, kind of a lack of training and awareness on the part of that person who allowed that to happen. When looking for related incidents that had to do with training, this one came to mind. Certainly, the San Bruno pipeline explosion had to do more than just with lack of training. But lack of training certainly in my opinion, was a contributing factor. Most of you probably heard of this incident on news, but may not be aware of how control and SCADA systems were involved in this incident. When going through the details of the NTSB reports, besides the fact that the basic summary was that the pipeline was overpressured, and a well that was in a pipe that was had been in the ground for well over 60 years eventually failed because of this overpressure situation. But when you dig further, you realize that the overpressure situation was caused by live work being done on a PLC. And so technicians were out servicing a PLC, and they replaced a block, and that somehow caused loss of communication. So back at the control center, operators were not able to see that PLC block had actually opened a number of bypass valves, causing the line going out of the station to significantly overpressure, sending high pressure gas down to the next station. And they weren't able to visualize this because they had lost communications, and the local operators apparently were not also aware that the technicians weren't aware that the valves had accidentally opened because of some kind of fault in the PLC due to their repairs, which ultimately led to the situation where the line was overpressured for over an hour and then eventually did fail. And even after the line failed, operators, because they were not aware and couldn't see, weren't able to shut off the source for almost another hour. So they were feeding this fire and explosion. So a very sad example of some of the problems that can occur due to lack of training on the impact of industrial communications, industrial control systems. So number 4 is segment the network, which is a very important part of the overall process, is making sure that you've applied good defense in-depth strategy, that you have multiple layers of protection to prevent outside influences, whether it be hackers or viruses or network disturbances, from making their way through your system and into the critical parts of your system. In the ISA 99/IC 6443, we call this zoning conduit modeling. So taking a system and partitioning it into security zones, as shown in this diagram here. In this case, we have an enterprise zone, 3 different plant zones, and within each of those we have a control system zone with increasing levels of security as we move down through the layers of the system. This is a pretty standard reference model courtesy of DuPont that shows the concept of zones, starting with a business zone, the computers and machines that would sit on in the office type environment. Then the plant or operations information management zone. Some might, in many examples, might call this a demilitarized zone because it's a layer sitting between the two, acting as a bit of a buffer, so that communications from the business zone can get its information out of the operations management zone, and the operations management zone gets its information from the control zone, process control zone, but the business zone and the process control zone do not have any direct communications. So that yellow layer acts as a buffer or a demilitarized zone. And then in the pink is the process control zone. And in the case of this reference architecture from DuPont, the safety system is also then partitioned into yet another subzone within the process control system. So what do we see when we do assessments in the area of network segmentation? I actually see a lot of variation here. Everything from systems that are completely air-gapped, meaning there is no network, no TCP/IP network connection from the office zone, office area, or office network to the control system. Though we don't see a lot of that. Most systems are interfaced, and unfortunately sometimes we see that the control system is actually sitting directly on the very same LAN as the office network. Other cases we see it on subnets, so it's VLAN or off of a router or a layer 3 switch. And then in the best case, we see firewalls between the control system and the office business system, which is in almost all standards and models is the preferred solution. So as said, we see everything from so we do see these air-gap systems. But most times these air-gap systems, I'd say really all the time, they always have some other form of network, other form of communication that would allow digital information in and out of the system. Very common, particularly in SCADA, distributed applications such as in power and water. We'll see these systems with modems, dial-up modems, and PC Anywhere or similar software. That is a digital connection and provides a conduit or a pathway or a vector for threats to get into these systems. So just because it's not connected to the network doesn't mean you're free from any form of digital communications. Of course, earlier we talked about USB drives and other sources. So air gapping is does not necessarily mean the system is secure. In fact, another thing that we're hearing about, particularly in the electric sector, is the use of unidirectional gateways or data diodes as a means of protecting the control system, connecting it to the office or business environment, but doing so in a way that communications can only go out from the control system and not in. And nothing wrong with the technology in terms of its ability to perform that function and to provide a safeguard, a very strong level of security on that boundary. The problem we're seeing is that many companies are viewing that as the silver bullet, the one and only solution for control system security, and that is a very naive viewpoint to think that just by preventing those bidirectional communications at that boundary, that the system, that nothing else needs to be done, for example, to comply with NERC-CIP or other cybersecurity measures like these 7 topics we're talking about today. An example of where insufficient network segmentation caused a problem in a plant is the Browns Ferry nuclear plant that was forced to scram because there were a number of variable frequency drives that were with Ethernet connections that were connected directly to the control system LAN, along with where all the PLCs and other automation equipment resided. And one of these variable frequency drives had a problem in its network interface card and started to basically chatter to send malformed packets or storms or some form of network disturbance that basically caused the entire control system LAN to fail and therefore forced them to scram the nuclear plant. So one of the purposes of network segmentation is to really isolate problems so that they don't spread and cause much more widespread damage, whether it be a virus or network disturbances or somebody who's infiltrated the system, network segmentation allows us to contain that and compartmentalize it. Point number 5 is controlling access to the system. That's making sure that we control who has both logical and physical access to the system. It involves making sure that we administrate that, we authenticate users, and we make sure that they're authorized. And a lot goes into access control. I don't have time to talk about the details, but I can talk about some of the common findings that we see. We are starting to see a lot more use of domain controllers as a method of providing single sign-on in control systems. And there's absolutely nothing wrong with that technology as long as it's properly deployed. In general, I'd recommend working with your DCS or control system manufacturer as to how they would recommend doing that. But one of the key things is to make sure that the domain controller resides within the control system environment and not up in the office or business area. So it's important to have a dedicated domain controller for the control system so that the machines there authenticate to that controller, but that communication does not need to leave the control system environment. So at a minimum, it should be in either on the control system, in the control system zone, the pink zone that I showed you before, or possibly in the DMZ, but that does require opening some holes in the firewall for authentication. Remote access is also a really big deal in control system security. It's a major area of vulnerability, and as we talked about earlier with policy and procedure, one of the things you really need to decide on is if you're going to allow remote access and how you're going to allow it. There are secure ways to provide remote access, but a lot of what we see in practice has a lot of flaws. For example, we do see a lot of VPN. VPN is very good at securing those communications over the wire so that they're encrypted and protected against common attacks like sniffing and man-in-the-middle attacks. But there are a lot of shortcomings with VPN, such as the communications going into the VPN, if they're corrupt to begin with, either if there's a virus or malware or hackers infiltrated on one side of a machine with a VPN client, then those communications will just go right through the tunnel. They'll get encrypted and they'll get unencrypted, but if it's a virus, it'll come out unencrypted and cause the same problems. So a few examples of some, I guess, things not to do with access control. One example was a public utility that had a fleet of service laptops and allowing their service personnel to VPN in. But for one reason or another, they decided the service personnel were not capable of launching the VPN client themselves and entering their credentials. So the machines were all set up to automatically start up the VPN client and log them in with stored credentials automatically. So something not to do. Another thing not to do is, of course, post the phone numbers for dial-up access in very public places, and also to use to not have things like PC Anywhere set up to auto answer. In fact, so use the security features built into those tools like callback and data encryption and other security measures that are available, but very rarely do we see them turned on. And and why? Here's an example of why. Here's a case of a hacker that was able to penetrate the SCADA systems in a water wastewater treatment facility. And the way this attack occurred was that an employee had brought home his company service laptop and was connected to his home internet connection and opened up a VPN to the SCADA system. The way the machine was set up, again, here's kind of what not to do, is the machine was set up with split tunneling enabled that allowed the employee to surf the internet while at the same time having the VPN connection open. And what happened is some foreign-based hacker, what appeared to be an attempt to set up a botnet, had infiltrated the employee's laptop, was installed malware on that machine, and then used the VPN connection to jump over to the SCADA machine and do the same on the SCADA machine. Number 6 is to harden system components. That is to remove, disable unused communication ports, turn off things like auto run on USB drives. There's actually quite a bit more you can do on USB, but I don't have time to get into other USB hardening techniques. Remove unnecessary applications and services, avoid file shares, patch the system when and where possible, and using, I talked about earlier about more secure ways to patch control systems. And where possible, use products that have been tested and certified for security, such as those that have been certified by through the ISA Security Assurance Program, which, if you're not familiar with, is a program that was launched in 2010, whereby manufacturers can submit their products to undergo testing, evaluation, and an audit of their software development process, all for security assurance. This is available both for products and now also available on a system level. So it includes a threat modeling or threat analysis of the control system, compliance with functional security requirements based on the IEC/ISA 99 standards, and a series of system robustness tests. So it's a program, if you're not familiar with it, you can go check it out at isasecure.org. So common findings here under system hardening. Unfortunately, though, many manufacturers do provide good guidance on security settings, recommended security settings. We're often not seeing those applied in the field. In fact, many times we see that even if the machine was delivered by the manufacturer with pre-hardened, we have seen a couple cases where that actually was removed when the machine arrived either by the IT department putting on their own image or a local system integrator doing so. We see a lot of standard IT images on control system machines that haven't been hardened for control systems. We see a lot of open, unused ports, and we see a lot of variety in patch management policies and practices. Good news, though, is we are starting to see at least more companies are aware of and working on patch management. Here's a case incident caused by PLCs crashing because of an IT security audit. An IT security professional was brought in probably by the IT department to scan the networks, and probably because of poor network segmentation, also scan the process control networks. And when they did so, they caused all the PLCs in the plant to hard fault. In this case, it cost the company almost $1 million, or more than $1 million in lost production. And lastly, point number 7: monitor and maintain. So once you've set up your cybersecurity program and have your safeguards in place, it's you can't unfortunately rest. You need to continually monitor and maintain, particularly in the area of cybersecurity, because the threats and the vulnerabilities are constantly changing and evolving. So we recommend installing the vendor's antivirus packages and updating those signatures regularly. Review your system logs periodically. There are not only, it can be hard to do that manually, but there are now tools like information and event monitoring, or security information and event monitoring, SIMS tools that can help with log correlation. Also, we're starting to see intrusion detection techniques make their way from the IT environment into the control system environment. Generally, what we're finding, if you just try to apply the IT products directly, you'll probably get frustrated and not be satisfied with the results. But there are some companies that are doing some unique things in terms of control system specific intrusion detection products and signatures to help look for signatures of communications that would be of concern to a control system. Penetration testing is something that we're starting to see more of in this world also. Again, there's some things to watch for here. You don't want to penetration test a live production system. This really should only be done at if the system is down for turnaround, or at FAT or SAT. But unfortunately, we do see cases where often driven by the IT department requests to have control system networks penetration tested, and there is an awful lot to be concerned about when doing that on a live production system. And so we talked about antivirus and making sure that that's maintained. Stuxnet by far is not the only piece of malware to infect control systems. There's been, in fact, malware is the #1 cause of industrial control system incidents. And this is just general viruses getting in, particularly at the Windows layer, it can cause very serious problems. We investigated one where an OPC server was completely compromised because of a virus. So it caused more than just loss of view. It caused loss of control. So common findings here in monitoring is that antivirus management policies and practices do vary quite widely. We are starting to see IDS and some technology installed. In many cases, it's not being well utilized or properly applied, but I think we're moving in the right direction in general, though. Vulnerability assessments have increased dramatically since Stuxnet. We are starting to see interest in penetration testing, particularly at when the system is either in commissioning or down for turnaround. And a couple examples related to that would be actually these examples look to be copied from the last one, so I'm going to skip those. And I'll give you the last incident before I close and answer any questions that I see. At least have one that has been typed in, and feel free to use the Q&A to type in some questions. The last is a virus infection that caused actually the one I just mentioned, the DCS OPC servers to fail. That virus was quite aggressive and required the machines had to be completely rebuilt from scratch, and so the plant was for over 8 hours was operating where the operators were largely blind, and a lot of things had to be in manual control while these OPC servers were completely rebuilt from scratch. So while you're thinking of your questions, I'll just put up the 7 steps one more time. And I'm going to check and see if we have any questions. As of right now, actually, I don't have any questions. If you have any questions, use the Q&A, and I'll try to answer those. Also, if you would like to, you can also send me your questions through email. I will actually try and put my email up while I answer. I do see one question coming in right now. I see a question, will you send the PowerPoint to us? Yes, we will send out a copy of the presentation for those that attended. I see a question, do you offer threat modeling training? Yes, we do. We offer threat modeling workshops where we do a combination of training and actual hands-on working with a team to go through an actual threat modeling exercise. So please contact me and we can talk about how that works. One question is, do you have any experience with the DuPont virus, which is it's been in the news in the last couple of weeks as a potential variant or of this Stuxnet virus? I don't have no, I don't. We don't have any hands-on. In other words, we have not seen it in any of the assessments we've done. It's very, it's relatively new, only in the last couple of weeks. We're staying on top of the information that's coming out from some very good sources, such as this Semantic guys and the Department of Homeland Security's ICS Cert. We're watching it very carefully, but it does not appear. Latest we're hearing is it does not appear to be a direct threat for industrial control systems. I do see another question here on, but I have to admit I'm not quite sure if I understand the question. It says, I understood that the FW and IDS IPS isolation of the trusted system is enough in most cases. Where full isolation or isolation by diode could really be necessary. So the question is, firewall and IDS IPS, is that enough in most cases? I would say yes, that is enough in most cases, provided the firewall has been properly set up, the rules have been properly applied, and communications have really been tightened down to those that are only necessary, and then followed up with good intrusion detection to watch for communications that would be outside of those bounds getting through. So as I kind of alluded to earlier, there are places where data diode or unidirectional gateways may be the answer. It's a technology solution among a field of technology solutions. What bothers me is when I hear that it is a silver bullet for NERC-CISSP compliance. No technology is a silver bullet for NERC-CISSP compliance or any cybersecurity program, because there are both technical and operational requirements. I hope that was clear from my presentation, with so many things being not technical, training, awareness, policy, procedure, access control. Those are not all technical. They require operational management as well as technical solutions. So if you want to make sure your program is comprehensive, you want to look beyond just technology. I just put up my email address. Hopefully you can see that on the screen, and because I forgot to put that on the first slide. But please, if you have any other questions related to this, feel free to email me, and I'll get back to you. All right, thank you everybody for attending, and for particularly on a Friday afternoon, at least where I am, or Friday morning, or Saturday morning, wherever you may be. But thank you very much, and stay tuned for other Exita cybersecurity webinars in the future.